Previously, we were talking about probability measures on an abstract sample space. So we would have a set, then we would have a family of events that form a sigma algebra, and we would have a probability measure that is defined on subsets coming from the sigma algebra. Today we're going to specialize to the real line, or sometimes this is helpful, to the extended real line, which I'm going to denote as R bar. That would be the real numbers with negative infinity and positive infinity. We're going to be primarily working with the real line, but you can actually extend many of these definitions to the extended real line without much of a problem. So this is what we talked about last time. We have a sample space, sigma algebra, probability measure on the sigma algebra. But today we're going to specialize to the real line. So we're going to have the real line. We'll have a real line. We're going to have a sigma algebra, and we'll have a probability measure on that sigma algebra. And the idea here is the intuition, one can say, is that we are doing random experiments with a real outcome. If you go back to the example that we did in a lot of detail, where we had the unit circle and we had a pointer that was randomly moving along the unit circle, then the outcome was not a real number. It was a complex number of norm 1. So that was a random experiment that's not describable by a real outcome. If you have two coins and you toss two coins, you can describe it as a pair of heads, a pair of tails, and then when they get interchanged together. So this is no longer a real number. This is a pair. And even if you denote this using binary ones and zeros, it's still not going to change the fact that this is not a real number. It's a pair of two integers. So random experiments that produce a real outcome, for those ones, the sample space would be the real line. An example of this is when you're waiting for the train to come. If you're lucky, then you have to wait 0 minutes. If you're unlucky, maybe you have to wait 15 minutes. But you can imagine intermediate values. Maybe you have to wait 2 minutes and 15 seconds, or 1 minute, 13 seconds, and some fraction of a second after that. So a random experiment that can be described using a real number, for those random experiments, this is what the discussion is going to be about. So we're basically specializing our previous discussion that we had from the previous lecture to the real line. Now let's say something about the sigma algebra. In the previous lecture, we talked about the unit circle and arcs on the unit circle. So we're going to actually do something very similar in this lecture. We're going to define this is called the Borel algebra of the real line, or you could also do this on the extended real line. So the Borel algebra of R is the sigma algebra generated by all intervals. So instead of arcs, these are going to be intervals. So this can be, now here the situation might be a bit trickier because an interval could be unbounded, right? You can go from like 0 to infinity. It could be unbounded. Of course, you can include or exclude the endpoint. So this is like an example of an interval. So finite intervals, open intervals, closed intervals. So if you start with the intervals, they will generate for you a sigma algebra. So how do you do that? Well, you start with the intervals. If you intersect two intervals, as you can see, you get another interval unless it's empty, in which case we call that a degenerate interval. They could intersect in a single point, but we call that a degenerate interval with just a singleton set would be considered to be an interval. If the intervals, If you take a union of two overlapping intervals, then you just get a larger interval. But if the intervals do not overlap, then you get a disjoint union of two intervals. And that will generate for you an algebra. To get the sigma algebra, then you have to then take all of those and consider what happens if you use countably many of them. So for example, Q, so Q would be a subset of the real line. This and Q would be an element of the Borel algebra. The reason for this is because the rational numbers, they could be written as a union of singleton points. But this is a countable set. And all of these are singletons, so they're in the sigma, so they're considered to be intervals. So Q is a countable union of intervals. That would mean that Q will therefore belong to the Borel algebra. We call it the Borel algebra, but it's really a sigma algebra. So maybe you can call it a Borel sigma algebra, but the terminology is just to call it the Borel algebra. So that would mean that Q belongs to this. This is fairly complicated. It's not too complicated, but it's a bit more bizarre of a set. And also, the irrational numbers will belong to the Borel algebra. This is an interesting example because I know that I previously talked about the Cantor set, but this actually works as well. So this is an interesting example because since this set is uncountable, it is not a union, a countable union of points, nor does it contain a, let's say, non-degenerate. So an interval that has any thickness to it, non-degenerate interval. So you cannot find, so if you take like A and B, if you take an interval where A is strictly smaller than B, then this interval will never be contained in the set of irrational numbers. The reason for this has to do with the fact that the rational numbers are dense. So no matter what two numbers you pick, between them there will always be an infinite number of irrational numbers. So you can never fully contain it in the set of irrationals. So this example illustrates that this is a fairly complicated set. In the Borel algebra, it is not a union of points, nor does it contain a non-degenerate interval. So you can get some fairly complicated sets in the Borel algebra. I'm going to show you another one later on, the Cantor set, which also falls under that. That's also fairly bizarre. Even more bizarre than this, you can argue. So that's the Borel algebra. And now I want to define a probability measure on this. So definition. A probability measure, P. I know that previously we talked about a probability space as being a triple. But in our current discussion, we've fixed to the real line, and we have fixed to the Borel algebra. So we will therefore talk about probability measures on a pair. A probability measure on the real line with the Borel algebra is a mapping from the Borel algebra to the interval to 0 to 1. And again, by the way, you can extend this definition to R bar, the extended number line, and then the Borel algebra would be the sigma algebra generated by all intervals in the extended number line. But we'll just mainly focus on the real line. So it's a probability measure on this pair, on this is your sample space, this is your sigma algebra. So it's a mapping that assigns a set in the Borel algebra, so in other words, an event. This is your event space. It's a mapping so that the following properties are satisfied, that probability of the real line is equal to 1, and probability of the empty set is equal to. Again, I did remark upon this, that from the properties of measure, this is going to be an immediate consequence from that one. But I'm not trying to make this the most efficient minimal definition possible, because we can use these interchangeably. So even though one can argue it is redundant. And then the second requirement is that if you have a bunch of events, and events are simply elements of the Borel algebra, are pairwise disjoint. So if you pick a bunch of pairwise disjoint events, then the probability of their union, countable union, would be the sum of their probabilities. This is an infinite series. It converges, and it converges to whatever this is. And the probability of this is just a number between 0 and 1. So these are the properties that are satisfied. Of course, as we remarked, if it is true for countable unions, this property is therefore also true for finite unions, because the empty set is in the Borel algebra, and any finite union can be extended to a countable union by just attaching empty sets at the tail and enlarging it into an infinite union. So that is the definition of a probability measure. Now, it would be helpful to also introduce the definition of a measure. This is a probability measure, but now let's define what is a measure. So if you've taken a real analysis course, you've definitely seen this before. So now let's remove the word probability. A measure, and instead of calling it P, let's call it mu for measure. On the real line with the Borel algebra, so it is a mapping that assigns an event, though at this point we usually do not call them events because we're not thinking of probability theory, we just call them subsets. It takes subsets, and instead of assigning it between 0 and 1, it rather assigns it to a number, to a non-negative number, including the possibility that it could be positive infinity. So it is a mapping, and this condition is now removed. That condition will now be removed. You're not going to say measure of R. You're not going to say that because it's no longer required to be 1. Rather, you can say that the mu of the empty set has to be 0. But this actually is a consequence of this one, as I'm about to show you, because you would say that if you have events, I'm going to call them events, even though we normally in real analysis do not call them events at this point. But if you have a bunch of events in the Borel algebra and they're pairwise disjoint, then the measure of their union is equal to the sum of their measures. And here you have to understand that it is conceivable that the series diverges, but it is a series of non-negative terms. So you're adding a bunch of non-negative numbers, and if there is no limit, then it just goes to infinity. So then, in this case, it is interpreted as being equal to positive infinity. That's the way you would interpret that. And by the way, the interpretation here, this should make sense, but I'll make it explicit. So the convention here is that finite plus infinity is plus infinity. So that's the convention that we're using. Because in contrast to using a probability measure, it could happen that some of these are equal to infinity. So it might happen that some of them are, let's say, a finite number, and some of them are an infinite number, but when you add them up, you would then have to interpret finite plus infinity to be infinity. And if this is a series where all of them are finite, it could still happen that the sum diverges. The reason for this is because on the left-hand side, the measure of whatever that is no longer required to be a finite number. So it could become infinite, and then the measure of whatever that is has to match, it has to be infinity, and it has to be consistent with that one. So that is where the distinction lies. This one is actually a consequence of that one for a very simple reason, that you can write the empty set as a union with itself, and that's the empty set. And then it would mean if you take the measure of both sides, the measure of the empty set plus the measure of the empty set is equal to the measure of the empty set. And by canceling it away, you're left with the measure of the empty set being equal to 0. So there's no reason for you to say that, but I'm just going to say that because it's a property anyway. If you have property 2, you have property 1 automatically. So this is what we call a measure. And the triple, so if you have a triple like this, well, actually, I should say that one can generalize, which we're not going to do, but one can generalize this and talk about triples. Talk about triples where you have a set. So instead of calling it omega, because we're not thinking of probability theory, we usually call it X. Then you have a sigma algebra, and you have mu. And these are called measure spaces. A measure space has the name that it has because the idea is that it is a space. So it is a set with the property that its subsets can be assigned some kind of measurement. They can be assigned a notion of size. So it's a way of measuring a size of a subset. And generally speaking, we do not talk about measures on all of the subsets of X because that would, in general, it would be impossible to satisfy all of these conditions. And so we compromise and we talk about a smaller collection of subsets for which we could do it, but we require that smaller collection of subsets to form a sigma algebra so we can work with infinite sequences at the very least. So this is not a class in real analysis, so we're not going to talk about this, but you can imagine how to generalize this. You have an arbitrary set, and on that set you have some sigma algebra, and the measure is then defined on the sets coming from the sigma algebra. But when you're working with the real line, the convention is, the understanding is that the sigma algebra that you're using for the real line is going to be the Borel algebra. You're going to use the intervals because the real line is, of course, something very special. A set in general does not have the properties of the real line. But when you are on the real line, because it is a real line, you can talk about intervals, and those are usually the kind of subsets we work with. So you generate a sigma algebra using those intervals, and that's how you get the Borel algebra. So when you're talking about measures on the real line, it's almost always going to be assumed these measures are defined on the Borel algebra. And these are the properties that you have. In general, of course, you can do this on an arbitrary set, but we're not going to go there because we will not need that. It's actually a very similar definition that we had for probability spaces, with the only distinction being that the measure is going to be taking values between 0 and positive infinity. And I would like to now define for you something called the Lebesgue measure. So let's remove this. So let's write this as a definition and as a theorem at the same time. You're going to see why it's definition plus theorem, because we're going to, basically what we're going to do is we're going to define something having certain properties, but one can ask, how do you know those properties are true? And that's where the theorem comes in. It asserts that this is doable. So here is our definition. The Lebesgue measure. So we need some notation to use. I've seen people use the notation lambda for Lebesgue. So the Lebesgue measure lambda is a measure on the real line with the Borel sets. Okay, so we know what a measure is with the property that if I is an interval, then the Lebesgue measure on an interval is just the length of that interval. So that is definition and theorem. So definition, it defines what is called a Lebesgue measure. So it's a measure with this property. It's a measure that calculates the measure of an interval by using its length. The theorem part, this is where the theorem part comes in. The theorem part asserts it is possible to extend this function, which, I mean, the idea is you want to measure the size of the interval. The most natural way to do that is to measure how long the interval is. Now, how do you find the length of an interval? So if your interval is of the form a comma b, and this is either, I'm going to write it like this, where this triangle bracket, it does not matter. It can either indicate the open or the closed bracket, and this can either be the open or the closed bracket, and you allow a and b to be infinite numbers, then the length of the interval would then be defined as b minus a. That's the way you would do it. It's no longer a probability measure because you can easily imagine intervals whose length is larger than 1, and you can imagine intervals whose length is infinite. The convention here would, of course, be, this is the reasonable way to do it, that if, let's say, b is infinity and a is a finite number, let's say 2, then infinity minus 2 would have to be interpreted as infinity. That's what you would do here. So you could have an interval of length infinite. But what you want to do is you're basically you are extending the notion of length to more complicated sets. So, like, for example, let me show you an example. Let's say I take the following set. Let's call it A. A is going to be the interval from 0 to 1 intersected with the rational numbers. So rational points contained in the interval from 0 to 1. What is lambda of A equal to? You're basically asking what is the length. Though length here does not really make sense because it's no longer an interval, but it sort of is a similar role. So you have the interval from 0 to 1, and then you only look at the rational numbers that make it up. And you can see from the picture that there is no interval anymore. It's just like a bunch of points all over the place. But how would you find the length? Well, what you can do is you can use the property of the measure to say that lambda of A would then be equal to the union. You would take singleton points of Q, where Q is rational number including 0, 1. That's what you would do. You are allowed to do that. This is a countable union. This is going to be important. This is a countable disjoint union. Oh, I'm sorry. I meant to say A is equal to that. And therefore, so thus, lambda of A would have to be equal to the sum of lambda of all of these singleton points, where Q is a rational number contained between 0 and 1. But because these are degenerate intervals, these are singleton points, this would just be 0. So it's a sum of zeros, and so the length of the set would be 0. That's what we're getting. So that is how the length has to, so I keep on saying length in quotation marks because it does not really make sense to talk about the length of that. But you could talk about the measure, the Lebesgue measure of that, because it generalizes the notion of length. We can also ask the same question, but with rational and irrational numbers interchanged. So we can, let's say we were to let B be the irrational number. So we would take the interval 0 to 1, and we would remove A. We would remove the set of rational numbers from that interval. So we're left with irrational numbers. And the picture looks almost the same. It would just be the interval from 0 to 1. But instead of having rational numbers, you'll have the irrational numbers in blue, right? And then the remaining ones that you removed are the rational numbers in red. And the two pictures look exactly identical. And it does not make sense to say that you have an interval because there's not a single interval, non-degenerate interval, that sits inside B. So, but what would its measure be? Well, so what is lambda of B? It appears that it should be 0 again, because the picture looks almost the same. But if you carefully work this through, this is what would happen. We have that A union B is equal to 0, 1. And so, because A and B are disjoint, that would mean that the measure of A, the Lebesgue measure of A, plus the Lebesgue measure of B would have to be the Lebesgue measure of the interval from 0 to 1. But because this is an interval, you calculate its length by just subtracting the endpoints. And we've said that the Lebesgue measure of A has to be 0. That was forced on us. And so, hence, the Lebesgue measure of the set of irrational numbers contained in 0, 1 would actually have to be equal to 1. So maybe you find that surprising that it works out this way. And you will notice that in doing these calculations, we're not using intervals whatsoever. We're just using the properties of the Lebesgue measure. Here we're using the property that we can write A as a countable union of singleton points, and then we can take advantage of the fact that the Lebesgue measure of a set is then the sum of all of those singleton points. That's how we got this calculation. And here we realize that the set of irrationals is pairwise disjoint with the set of rationals, which then allowed us to again reuse the same property again, that the Lebesgue measure of the union would then be the sum. And that's how we got this calculation. So all of these numbers are forced upon us if we're willing to accept that it is possible to define such a function on this larger set. So not on the set of intervals, but on the Borel algebra, on the set that on the set which is the sigma algebra generated by all of those intervals. So that would be the value of. So that would be the Lebesgue measure of these two bizarre sets that we have here. But it comes down to the question about how do you really know that you can do this? How do you know that this exists? So we're not going to justify this because the proof is almost the same as it was the case. So as we did the previous one on the unit circle. I guess I should say one more thing before I go on. It's not important for us, but maybe I should just make a comment. If you're reading this in some kind of source, maybe you'll be confused by this. Here's a comment. It is possible to extend lambda to an even larger sigma algebra. I guess people call it, I think the notation people use is script M, and they call them the measurable sets. Some people call them the Lebesgue sets. And so you would write that you have, this is your set, this is your sigma algebra, and this is your measure, with the Borel algebra being actually properly contained in this larger sigma algebra. But this larger sigma algebra does not extend to the power set. So that will be strictly smaller than the power set of the reals. So it's not every subset, but it is possible. But we really do not care. It really does not do anything for us. In practice, one deals with the Borel algebra anyway. So in some cases, it is possible that your measure can even be enlarged to a bigger sigma algebra than the Borel sets, but you're always going to have the Borel sets no matter what, because we want to work with intervals and we want to work with sequences. And if you work with intervals and sequences, the Borel algebra is going to be the absolute smallest algebra you will always have, no matter what you do. In some cases, depending on the measure, it can be possible to even extend it on every subset, on the entire power set. But we'll always talk about the Borel algebra because that will be sufficient for all of our purposes. So I just wanted to just get that out of the way, because maybe if you're reading a book on measure theory, they would talk about the Borel algebra, then they talk about the measurable, the algebra of measurable sets. And if you're wondering what they're talking about, they're just really said the measure is actually, can be defined on an even larger algebra, but it really is not going to do anything for you. So we'll just keep it simple and we'll just pretend that we have the Borel algebra. The question here is, how do we justify? We justify that this lambda exists. So this is the quick answer, which we're not going to get into. The quick answer is that you're going to use the Carathéodory extension theorem for measures. So there is a extension theorem for probability measures that we mentioned, but there's a very similar theorem for measures. In fact, usually the extension theorem is for measures, and then you specialize it to probability measures. But we actually did that more carefully last time on the unit circle. So if you recall, we went through the process that we have the unit circle, and if you start with arcs, and those arcs generate for you a sigma algebra, okay? And we went through the process to show that the length function on arcs can then be extended to that sigma algebra by verifying the continuity of probability measure. So you would have to do the same thing over here. It's almost the same proof, in fact, almost the same proof. So because of that, we will skip this and we'll just accept the fact that such a measure exists, and it's called a Lebesgue measure. And intuitively, it generalizes the notion of length. Now, before we go on, I wanted to just say one last thing about measures, and then we'll talk about integration. That's going to be used a lot, integration. But actually, I'm going to do an example with you first before I go to integration. But I wanted to just finish up with the measure stuff. So recall that if omega, then you have script A and P is a probability measure. Then we have something which we call probability measure is continuous. So this is a property that we mentioned. The idea here is you're basically trying to say that if you take the limit, if you take an event f that approaches an event e, and you take the limit of all of those probabilities, that should give you the probability of e. So that is what we're trying to say. Now, this is not rigorous, of course. This is just intuition, because it's similar to continuity the way you see it in calculus. But to make it more rigorous, so more rigorously, if, let's say, En are in your algebra, and you have a sequence of events. So there's different ways to formulate it. I'm going to do it in a decreasing way. And your sequence of events are decreasing, and their intersection, the intersection of all of them gives you E. Then the probability of En will converge in the limit to the probability of E. And we proved that. That's actually not difficult to prove. So, however, when you talk about a measure space in general, so let's say this is X. I know that's not what we're going to be doing because we're focusing on the real line, but if you have an arbitrary set, and on that set you have a sigma algebra, and on that sigma algebra you have a measure as opposed to a probability measure, is a measure, then we do not necessarily have, continuity of measure. And I'll give you an example. So what do we mean by continuity of measure? It means this, that if En are in your sigma algebra and En decreases down to E, then the measure of the En will converge in the limit to the measure of E. That's the, yeah, that would be the continuity property. The simple reason why it works for probability measures and not for measures is because with probability measures, you always have a number between 0 and 1. So you're always dealing with finite numbers. But you have to understand that with measures in general, they're not required to be between 0 and 1. And that might mess up. So if you go back to the proof that we did for continuity of probability measures, we're actually using the fact that they're finite. And that's important for us. But here, that's not going to work, right? We're going to have infinities everywhere and in general, and that is what's going to violate it. Let me just show you a very simple example that you might find helpful is we're going to have n. This is going to be the set of natural numbers. And the algebra here, this is actually going to be the power set. This is going to be the power set of the natural numbers. So it's actually going to be every subset of n. So this is one of those circumstances, well, you'll be able to define the measure on every subset. Not always doable, but in this case, it'll be doable. And you'll have what is known as the counting measure. And mu, and if E is in A, so in other words, it's just a subset of the natural numbers, we define mu of E to just be the number of elements in E. And this goes by the name of the counting measure. I mean, it's a nice example of a measure. It nicely fits with our intuition of what a measure is supposed to do. It's supposed to measure how big a subset is. Well, if you're working with the natural numbers, what's one reasonable way to measure how big a subset is? You just count how many elements you have there. And that number is either a finite number or it's infinity. If it's an infinite set, then mu of E is just equal to infinity. So that's what you do. And it is easy to verify. I leave that up to you to think about, but it is, well, I mean, basically, what happens when you have a disjoint union? If they're non-overlapping, then the number of elements, you just add up how many you have. So it's like, so there's not really much to be done here, but this is called the counting measure. Okay, and we claim that this measure is not continuous. So look at these sets. Let's define En as the natural numbers, and then we're going to take away everything up to n. Okay, so then E0, so this will be every natural number excluding 0, and E1 would be every natural number excluding 0 and 1. This contains that. This contains E2. That contains E3, and so on. And their intersection, if you were to intersect all of them, then you're basically asking the question, what if you remove, because you're going from 0 to n, and n goes to infinity, so you're removing every natural number. Well, as n goes to infinity, you end up removing every one of them. So the intersection of all of them is just going to be the empty set. This is going to be the empty set. And now you can check, and then you have to check if the limit as n goes to infinity of mu of En is that equal to mu of the empty set. Well, mu of the empty set, that's just going to be 0. But on every level, these are always infinite sets. And then you're saying the limit of this sequence of extended numbers converges to 0. That's clearly not true. So a fairly nice example that illustrates that this nice property, we have it in probability theory, but we do not necessarily have it in general when we're working with arbitrary measures. Now I want to give you an example of a measure. This example is referred to as the Dirac measure. The Dirac measure. We're going to pick a point on the real line, and we're going to construct the following probability measure. This is going to actually be a probability measure, as you will see, on the real line with the Borel algebra. Now, the thing with the Dirac measure is it's very easy to generalize this, as you're about to see, very easy to generalize this to any measure space. So for any set and for any sigma algebra, you can do this. Here's the way it is defined. We're going to primarily focus on the real line, but you can really do this for anything. So we're going to construct the following probability measure. This probability measure is going to be denoted by the symbol delta, delta for Dirac, and we can indicate the point that is being fixed. This is sort of the fixed we pick, or you can say fix. So for an event in the sigma algebra, we define the Dirac measure of that event to be equal to. So if it's clear what the point is, you often never even reference it, but I'll reference it here. The Dirac measure of an event, it's equal to 1 if the point is in the event, and it's equal to 0 if the point is not in the event. So that's called the Dirac measure, and it's a very easy exercise, and I'll put this on the homework to show that delta P is a probability measure. In fact, on the power set of the reals. As I've indicated before, when we work with probability measures on the real line, there's no harm in always talking about the Borel algebra, but sometimes you do have measures, like for instance, we just previously mentioned the Lebesgue measure that could be defined on the larger sigma algebra. The Dirac measure can actually be defined on maybe we call this the power algebra, the algebra of the power set. So you can really define it on every subset, and it will satisfy the properties of being a probability measure. We do not really care that you can go larger than the Borel algebra, but this is something you can check. It's a very easy exercise. You just go through the definitions. You can see that by construction, the probability, the Dirac measure of an event, is always 1 or 0. So these are like the two extreme cases you can have when you have a probability measure. So that's the way it is defined, and then we can generalize this. So then we can generalize this procedure by picking two things, by picking a subset, non-empty subset of the natural numbers. You're going to think of this as an indexing set. So this is either finite or countable. So this is an indexing set, and you pick a collection of real numbers that are positive. You can think of these as weights. You will see what I mean and why I call them weights. Positive, so that the sum of all of these add up to exactly 1. So if this is a finite indexing set, then this is just a finite sum. If it's an infinite indexing set, then you have to interpret this as an infinite series. And by the way, this infinite series, if it converges absolutely, because these are positive numbers. So then the issue of rearrangements does not matter. But here, there's not really an issue of rearranging the terms of an infinite series, because if these are indexed by the natural numbers, then you just order them in their natural ordering of the natural numbers, and that's the way you take the sum. But even if this was a different kind of indexing set, let's say you were using rational numbers and they added up to 1, then because the rational numbers is a countable set, you have to choose a particular ordering to describe the rationals in some kind of sequence. But no matter how you do it, the infinite series will always converge to the same number. But anyway, you pick a bunch of weights and you make them add up to 1. And then we can construct a probability measure, let's call it P, on the real line. with the Borel algebra as follows. So the probability of an event will be defined as summing up. So you will sum up. You'll have these weights multiplied against. So there's one more thing I forgot to do. I should have written it over here. So we pick a bunch of numbers that are called weights, and we pick something else. And we pick a bunch of points on the real line. We pick a bunch of points. Maybe we'll say distinct. We pick a bunch of distinct points. Not that it would actually really matter, but you can just assume that they're distinct. You pick a bunch of points on the real line, and then you construct a probability measure by using the Dirac measure concentrated at every single one of those points. And then you evaluate on the event. So this is sort of the shorthand notation, is you simply say that the probability measure is the sum. It's the weighted average. That's what it is. It's the weighted average of all of these Dirac measures. That's why we're calling these weights, because this is indicating the intensity with how much every point is to be considered. And this is very easy to prove that this is a probability measure. You just have to go through the definitions. Now, what is this supposed to represent on an intuitive level? Okay, so what does this describe? What does this probability measure describe on an intuitive level? So to illustrate this, let's go back to our example. So we had this example from our previous lecture where we had a cone. We had this cone in the shape of a die, and our sample space consisted of numbers from 1 to 6. So there's 6 sides, and you label each of the 6 sides by numbers from 1 to 6. And the base, we labeled that by the number 6. And the random experiment is we take this cone and we roll it, and it will randomly land face down. And it can land on its base, its pentagon face, or one of the 5 triangular faces. And we've just made up a bunch of numbers just for the sake of concreteness. We've said that we're going to assign the number 1/2 to the number 6. And this is supposed to represent the fact that 50% of the time this cone lands on its base, 50% of the time. Of course, there's no way to mathematically know this, because whatever the appropriate numbers need to be assigned to all of these very much depends on the geometry of the cone, because this cone, in contrast to a cube, is not symmetrical anymore. So there's no reason for you to think why you have to assign the same number to each of the 6 faces. But let's say the other 5 faces are equally likely because they're symmetrical. So the remaining 5 numbers have to add up to 1, and 1/5 of that would be 1/10. So the remaining numbers would happen with probability 1 out of 10. Now I want to remind you something about something very important, that usually in probability theory, when you're doing random experiments, the probability of a single point, more rigorously the probability of a singleton. So in general, if you pick a point in any sample space, then the probability of that singleton event will happen with probability 0. This is what we saw happen in the random experiment when we were on the unit circle and we had a random pointer moving around, that the probability of the singletons happen with probability 0. That's the only appropriate way to interpret that. However, there are random experiments that are a lot simpler to understand, like this random experiment that has a finite list of outcomes. So when you have a very simple random experiment, then the situation is a lot simpler, that you can actually analyze probabilities of events by focusing on the individual sample points and assigning the appropriate weights so that they add up to 1. Of course, in general, this is what's going to happen. As you will see throughout the course, this is usually going to be the situation that we're going to be in, because when you're dealing with uncountable sample spaces, that is usually what happens. And as you can see in the very definition of this, you are choosing an indexing set. It's important that it's either finite or countable so you can form the series. So when you're dealing with countably many things, you can often get away with this kind of analysis where you can just assign weights to each of the sample points. But here's the idea. It is okay, since this sample space is contained in the real line, we can describe the random experiment by using the real line instead of omega as the sample space. You might find this a bit bizarre because you would say, why would you do that? You do not have to do that, but I'm just saying that because these happen to be real numbers, you can just describe this random experiment by a point on the real line. It just would happen that most points on the real line would just never happen. So for instance, if you pick a negative real number, you will never see that. But it's still correct to say that whatever random outcome you get, it always ends up in this set of numbers. Okay, so your sample space would be the real line. Your sigma algebra would consist of the Borel sets, which is also a bit unusual because normally, because this is the sample space, you would consider subsets of this sample space. Like, why would you go any further? Why would you ask for the probability of getting the number 7 if there is no such side? But you can still ask. It's just going to happen with probability 0. So there's nothing really wrong with writing that. It just might be a bit unusual. But I'm writing this intentionally because this entire class is dedicated to probability measures on the real line. So I want to intentionally describe everything using this specific notation. So this would be your Borel. So this would be your sample space, your sigma algebra, and now we need to describe the probability measure, where the probability measure would be described as follows. That these are the only points that matter, and then you would just say it's the sum of 1/10, then you will write delta 1 plus 1/10 delta 2 all the way up to 1/10 delta 5, and then you would write plus 1/2 delta 6. So this would be a probability measure on the real line. So this is this weighted average of Dirac measures. And if you think about it, this makes sense. Like, let's say my event consists of the event of even outcomes, 2, 4, and 6. If you calculate the probability of the event, you would have to apply each of these Dirac measures on this point. But when you apply this Dirac measure to that point, that is 0 because 1 is not an element of this event. So that would be 1/10 times 0. Then you would have plus 1/10. For this one, because 2 is in there, you would rather assign the number 1. 2 is an element of this event, so you would assign the number 1. And then it would be 1/10 0 plus 1/10 1 plus 1/10 0. And then finally, when you reach the last one, when you reach this Dirac measure, you can see that 6 is included in the event. So the Dirac measure applied to the event by definition would be equal to 1. And so you would have 1/2 times 1. And if you rework the math, that would just be 1/10. So yeah, 1/10, that would just be 2/10 plus 1/2, which makes sense, right? Because you have 2 sample points that happen with those probabilities, and you have 1 sample point that happens with that probability. So you can see what the Dirac measure can be used for. It can be used for describing random experiments that have a finite number of outcomes or a countable number of outcomes. That's basically what it gets used for. And we can even make this definition that, let's make this definition. We say that P is a discrete probability measure on the real line if and only if P is a sum, maybe we can say a weighted sum of Dirac measures. So, of course, this is either a finite or countable, because otherwise it's not going to make sense. You cannot form an uncountable series. That would not make sense. So this is how we can define what we mean by a discrete probability measure. There's other ways of describing what we mean by a discrete probability measure, but this is like one way to do it, one of the equivalent ways to do it. This is not usually what we're going to do. Like the kind of probability measures that we will be using will be more complicated than this. But this is just to show you that this is a type of possibility that can happen. So the next thing that I want to move to is I want to move to integration. So here's what we're going to say. We can create a theory of integration in general for, and here let's keep it as measure spaces. Measure spaces. So you would have a set. On that set, you have a sigma algebra. And on that sigma algebra, you have a measure. So notice we're saying measure, we're not saying probability measure. Of course, a probability space is a special type of measure space. So that means that when you have a probability space, everything that we're saying is going to be applicable. But it's convenient to generalize this a little bit further and allow a notion of a measure space. So let's assume that we have a function from x into the real line. Okay. Actually, sometimes people allow the function to go into the extended real line with very straightforward modifications, but let's keep it simple. So we have a real valued function. This is a real valued function. It does not have to be continuous. In fact, it does not even make sense to say what it means to be continuous because X is not a topological space, though you can use the sigma algebra to create a topology. It's just not a very interesting topology. So we just have a real valued function. And we would like to define, so for an event E in the sigma algebra, we want to define what it means to integrate the function over that event. And this is assuming this integral exists as a finite number. We of course know that you have certain functions that cannot be integrated, but part of the theory of integration is knowing which functions could be integrated, and secondly, how integration is defined and how it is computed, and things like that. Now, I'm just going to say this, that the theory of integration for measure spaces takes an entire chapter in a real analysis book. And we only have a single class to talk about this. And I do not want to get into the theory of integration because that's not appropriate for probability theory. In my experience, a lot of courses in probability theory, they just completely branch off into real analysis, and like 90% of the class is in real analysis. And by the time you return back to probability theory, you only have like 2 or 3 classes left, and all of the interesting probabilistic stuff disappears. I think that's a very wrong way of teaching probability theory. If you're teaching probability theory, you're teaching about stochastic processes, that has to be your priority. This is not probability theory. It is used in probability theory, but it's not probability theory. And because of that, it's just not appropriate to carefully discuss the theory of integration. So what I'm going to do is I'm going to give you an overly simplified explanation of what integration is that you will hopefully find satisfying and that you can accept, and we can move on and we can use it when we need to use it. Fortunately, we're all comfortable with integration. We're all comfortable with integration on the real line. And this is just a generalization of that to measure spaces. That's all what that is. So here's the very quick outline. This is an overly simplistic outline of integration. But like I said, hopefully you find this to be satisfactory enough. So we're going to make an assumption. So we will make a technical assumption. We'll make a technical assumption that, so we're going to assume here that X is what we call sigma finite. So sigma refers to countable, and finite refers to having a finite measure. So every probability space will automatically be sigma finite, as you're about to see. So here's what it means. If and only if X can be partitioned. So partition means written as a disjoint union. As a disjoint union. So X can be partitioned into events with En in the sigma algebra, and the measure of each one is finite. So that's the definition of what it means to be sigma finite, that you have finite measures and you have countably many events that decompose X in such a way. Now, the go-to example of something that is sigma finite is clearly R, so the real line with the Borel algebra and the Lebesgue measure is sigma finite. Why? Well, because you can write the real line as the following collection of intervals. 0, 1, then you write union, 2, 3. It does not really make a difference how you do it. 3, 4, like this, 3, 4. And here you would write, of course, 0, -1, union like this. And you can see that you've decomposed your sample space into a disjoint union of events. Each of these are in the Borel algebra because they happen to be intervals, and the Lebesgue measure, when you apply it to each of these events, happens to be a finite number. Okay, so this is the technical assumption that we make here, that our measure space is sigma finite. Now, if you have a probability space, this is automatically true, because if you have a probability space, then the property of a probability measure is the probability measure evaluated on the entire space gives you 1. So that means you can partition this with just a single event, namely just X itself, and then you can choose the remaining ones to just be empty sets. Okay, so you can always do integration. Well, I have to be a little bit careful. I'm not saying you can always integrate every single function, but what I am saying is you can do this kind of procedure of talking about what integration means, right, how it is defined in a probability space. So that's going to be the technical assumption. And here is what you're going to do next. So the idea of integration, and this is the way you see it in advanced calculus, is that it is a limit in some way. It is the limit of sums, of approximating sums. So you approximate the sum, you form a sum, and that sum approximates what the integral is. Okay, so let's do this. So let's assume that f is a function. It's a real valued function. And we're going to write, and we're going to partition X as a countable union of events. Maybe I should just call them Xn, with the measure of each one being finite. Okay, so then you're going to pick a sample point in every one of these, in every one of those sets that partition X. So maybe I should draw a picture. The picture here is, imagine that this blob represents X, and you're just cutting X, you're partitioning X into pieces, and then in each one you're picking a sample point. This is like X1, this is X2, this is X3. So this should remind you of Riemann sums that you do in calculus. The only distinction is is that in a calculus class, you're partitioning an interval, right? You partition an interval into subintervals, and in each subinterval, you then pick a sample point. But other than that, it's the exact same idea. When you're dealing on the real line on an interval, then when you form the approximations, when you form those Riemann sums, you're multiplying the height of the function by the thickness of the subinterval. This is going to be the same thing, but thickness is just going to be replaced by measure. And so you're going to pick these sample points in each one, and then the idea is that the integral of your function over your space x is approximately equal to, you would form the sum, you would do f evaluated at xn, and you would multiply it by the measure of every one of those sets from which the sample points are chosen. This is why you want these to be finite. So these are finite numbers. This is a real number. This is real. That's a real number. And you are multiplying a real number by a finite number. So you're having this is a real number, and then this is an infinite series of real numbers. Now, it is conceivable that maybe this infinite series does not converge, but the idea would be that if the series does not converge, maybe if you chose a different partition, you could make it converge. And the whole point of integration is you keep on making these smaller and smaller and smaller. You just keep on shrinking these. And what's supposed to happen is that, so the overly simplified explanation is that we say that f is integrable on x. And by the way, I'm talking about being integrable on x, but you can really do this as being integrable on any event. But let's just keep it on x. Integrable on x if and only if the approximating sum, right? Let's call it the Riemann sum. That's the approximating sum, converges to the same limit, no matter how smaller we pick those. We pick the xn's in the partition. So you keep on making the partition smaller and smaller and smaller, and no matter how you do it, no matter how you choose it, it will always give you the same thing. And the limiting value of all of that is what you call the integral of your function. Now, if you have taken an advanced calculus course, you probably recall that making this idea that the Riemann sums converge to the same limit is the part that's a little bit tricky to make rigorous. So there, like in advanced calculus, normally what you do is you probably remember talking about upper sums and lower sums. You approximate Riemann sums from above and from below, and then you consider the supremum and infimums of all of them. And if they give you the same thing, then the idea is that these approximating sums will then converge to the same thing. So it is fairly technical to actually write out those details, and it becomes even more technical to write out the details when you're working general measure space. And I really do not want to go there, but this is a very simple overview. I guess I should have said maybe one more thing, that I wrote the integral of fx, but maybe it would have been a little bit better to write it as, in this case, it's not really ambiguous because you only have one measure, but usually what we write is write d mu. We write the integral of the function over our measure space with respect to the actual measure, and then as you can see, it's being replaced by a sum. The function is being evaluated at the sample points, and it's being multiplied against the measure of all of the events in the partition. Okay, and that's basically the way we do it. Now, fortunately for us, a lot of our integration will happen on the real line, right? So for us, usually x will be the real line, and the measure will be a Lebesgue measure. So we will talk about the integral over the real line of a function with respect to the Lebesgue measure. This is also denoted by, this is the way you commonly write it, is you write it maybe the integral from negative infinity to infinity, because that's the real line, and then you write f of x dx, right? That's probably the way you normally write it. This is the way you're used to writing it, but this is really what we're saying. We're specializing, for in most cases, we're going to specialize to the real line by using the Lebesgue measure, okay? And that's what we're going to be doing. So because of that, we're going to be fairly comfortable with this. And as I indicated, this does take a lot of effort to prove. I'm sorry, a lot of effort to define. And after you define it, it takes a lot of effort to prove the properties of integration. That's why it takes an entire chapter. So what kind of properties of integration are we talking about? Well, it's the properties that you can probably guess that if you have an integral of a sum of two integrable functions with respect to a measure, that they would be, if they're both integrable, the sum is integrable, and furthermore, the integral is the sum of the integrals. If you have a scalar multiplied against an integrable function, then you can take the scalar out, and that would be the result. If one function dominates another function on x, then the integral of f d mu would be greater than or equal to the integral of g d mu. This is the monotone property. So this is linear, this is linear, this is monotone. So the properties that you can expect, they just take effort to prove, right? You actually have to go through the definitions to prove them. And I think it's just much more convenient for us to just have this overly simplistic explanation of integration, so we can just write it out, at least give a little bit of service to how one defines it, so that if you're interested, you can then later on, after the course is over, go back to a real analysis course or open up a real analysis book and see how it is done more carefully over there. And that will permit us to get more rapidly into probability theory that we're really trying to get to. Now, I want to show you an example. Let me finish with this example on integration. Let delta 0 be the Dirac measure on the real line with the Borel algebra. Okay, so we have this. And let f be a real valued function. Yeah, actually, let's do this. So let E be a Borel set, and f is a real valued function. The question here is going to be this. So if you're not sure what I mean by a real valued function, I just mean to say it's a function defined on R. In fact, it does not even have to be defined on R. It can be defined on E. Does not matter so much. The question here would be this. What is the integral over f over E with respect to the Dirac measure? What is that equal to? So you can try to test your intuition. So you can, if you want to, you can pause the video, try to work this out. You can try testing your intuition. So here's the answer. Let's pretend that E is an interval. It could be more complicated than an interval, but let's pretend that E is an interval. And we're going to partition E into subintervals. We're just going to cut it up into pieces. Okay, I'm going to cut it up into pieces like this. And then in each piece, we're going to pick a sample point. They could be anywhere. They could be in the middle, they could be to the left, they could be to the right. It doesn't really matter, but you end up picking the sample points. And so you partition it, so you're writing E as a disjoint union of En, and you're picking a point in every En, assuming that these are non-empty. If they're empty, you just disregard them. Then you have a finite, then you might have a finite sum, doesn't really matter. So you pick points in there, and then you would say that this integral over f with respect to the Dirac measure should be approximately equal to the sum over n f of xn multiplied by the Dirac measure concentrated at 0 at En. So 0 here is just the origin on the real number line. So let's indicate, so one of these is going to contain 0. Let's actually assume that 0, let's assume that 0 belongs to E. Otherwise, you will get a different answer. Let's assume that E is 0 somewhere. So let's say that, let's draw a 0 somewhere. Let's say 0 is located right over there. Let's say that is 0. So you will see that every one of these events that do not contain 0 will have 0 measure, right? So this drops out, that. So all of these drop out. It's going to be 0. And in the end, you will just have, this is a sum of zeros, because all of these measures are 0, right? Because 0 is not in that particular event. So, but the one that contains it, it's equal to 1. So then that would be equal to f of, so it'll be f of, let's say P, where P is whatever point that is, f of P, multiplied by 1, because in this case the Dirac measure is equal to 1. So it's f of p. But p, where p is close to 0, right? Because p has to be included in that subinterval. And then you make it smaller. So as we make the partitions smaller and smaller, p becomes 0. So thus, based on our intuition, this integral should be exactly equal to, so this is going to be the limiting procedure. These are just approximations. So it's approximated by f of p, where p is a point close to 0. But as you use more of these, p approaches 0. So this should be f at 0. So it should be f at 0. So that's the way that it works. So basically, when you integrate a function with respect to the Dirac measure, all of the values of the function throughout that event are disregarded, and you look at the point where the measure is completely concentrated. You select that one point, and you evaluate the function at just that one single point. So I think this is a fairly nice, intuitive example that illustrates how this works. But of course, if you want to make this more rigorous, this will take more effort, because you will then have to go through the more careful definition of how integration works. But these are the kinds of arguments that will be okay for our course, because this is closer to real analysis than it is to probability theory. So with that, we can now move to a new topic that will be important for us. Now we're going to discuss a general method that constructs new measures. It would be helpful to first talk about measures, and then we can easily specialize that to probability measures. So this is going to be a method that will construct new measures using integration. So once you know how to integrate, you can use integration to create new measures. So we will, of course, exploit properties of integration. Properties that are very believable, but we're not going to prove, because in my defense, as I said, that's really appropriate for a real analysis course. So here's how this is going to work. So let x comma a comma mu be a measure space. I'm going to make this a little bit more general, but for our purposes, it would be good enough, if it makes you feel better, to assume that the sample space is the real line and the sigma algebra is the Borel algebra, and you have a measure that is defined on the Borel sets. But you can do this more generally. Be a measure space, and maybe we should add, that is sigma finite, because we want to be able to talk about integration. So the way we explained integration, the intuitive way of partitioning your space into a countable collection of finite, we're partitioning it into a countable collection of sets that have finite measure, and then we use that to form an approximating Riemann sum. So that's where this comes in, because we're going to be doing integration. And f, this is going to be a non-negative function. Non-negative function that is integrable with respect to mu. So in other words, that just means that the integral of f over x with respect to mu, that this exists. Because just like we learn in advanced calculus, you can find these pathological examples of functions that are not integrable, but they do not even have to be pathological. I mean, you can just easily imagine, just to use a very easy example, like here's a very innocent type of a function. Let's say you have the real line, you have the Borel algebra, and you're using a Lebesgue measure, and the function is defined by the formula that f of x is equal to x squared. Well, if you try to integrate this over R, f with respect to the Lebesgue measure, well, this is not going to exist, because what would happen if you try to integrate x squared from negative infinity to infinity? Well, this is just going to blow up to infinity. It's not a finite number. So, and this is not even pathological. But there are functions. So functions are not necessarily integrable, but we're going to assume the function is integrable and it is non-negative. We can define, we can construct, maybe I should say, we can construct a new measure on x. And like I said, if it makes you feel better, you can just pretend that x is the real line. But in this case, it's not any more difficult to be a little bit more general. In fact, sometimes the interesting thing happens in mathematics. By being a little bit more general, it might be even easier to see something, because then you're not focusing on the special structure of something that's more specific. So we can construct a new measure. Let's call this measure, let's give this measure a name. So you have mu, so that's like the letter M in Greek. So the letter N in Greek, it's nu, and I think this is the way we write it. It looks like a V, so it's going to be a little bit tricky to write. A new measure, nu, as follows. So here's how you do it. So you pick an event in the sigma algebra, though I should say that when you're doing probability theory, you call it an event. When you're doing measure theory, you sometimes call that a measurable set, if it's coming from the sigma algebra. It is a bit confusing because the word measurable set means two different things. It could mean measurable set in the sense of a Lebesgue set, but it could also be measurable set in the sense that it's coming from the sigma algebra. But let's just call it an event. So you pick an event in the sigma algebra, and then we define nu of E to be equal to, by definition, this is the way we're defining a new measure, that this is equal to, we're going to integrate the function f with respect to the original measure that we currently have, and we're going to integrate it over this smaller event E. Now, this is the part which is going to be important why the function is non-negative. The first reason why this is important is because if the function is integrable on all of x, and this is a finite number, then the property of integration will tell you that if you're integrating it over a smaller set, it has to be bounded by the integral over f d mu, because you're integrating a non-negative function over a larger set. So this is what I mean, we exploit properties of integration. We all know this from real analysis, that if you integrate a function over a larger interval and it's not negative, its value will only get bigger. And of course, we're just taking advantage that the properties of integration properly generalize to a more abstract measure space. Though we're not proving it, I think this is believable. So this would therefore be something that's finite. So this is going to be less than infinity. And so whatever this is, it's a non-negative function integrated over a set. So therefore the integral will be something that's finite, and therefore this exists. So in particular, the measure that we're constructing is a finite measure because it's always going to give you a finite number. Even though the original measure mu does not need to be a finite measure. Mu applied to all of x could be infinite. However, we're integrating using this function, and we're making the explicit assumption that it is conceivable that mu on all of x is infinite, but when you integrate over the function, it is not. Like, you can easily imagine examples like this. So for instance, when you integrate from negative infinity to infinity, and you integrate the function e to the negative absolute value of x dx, this function looks like something like this. And it's not hard to work this out. I think it's equal to 2. I think that's equal to 2. But you can see the function being integrated on the real line results in 2, even though the Lebesgue measure, the usual Lebesgue measure of the real line, is still infinite nonetheless. So that's okay. So in particular, this nu is a finite measure on X. That just means finite measure just means that it's finite on the sample space. And also, and then clearly, nu of E is non-negative because you're integrating a non-negative function. So thus, nu provides for us a mapping from the sigma algebra into the non-negative reals. I mean, there's nothing wrong with including infinity, but we're never even getting infinity. So we're getting a finite number. So we have to check. So we need to check that nu is countably additive on disjoint unions. So this is the property that a measure is supposed to have. So you take a bunch of events that are pairwise disjoint, and you take nu of those events. So that is going to be the integral over the union. So let's write it as E0 union E1 union E2 union. And then we're integrating our function with respect to mu. And now we use another property of integration. This is just one of the properties of integration, that if you integrate over non-overlapping sets, then that's the sum of all of the components. So that would just be the integral of E0 over f d mu plus the integral of E1 of f d mu, and so on. And if you write back what this is nothing more than nu applied to E0 plus nu applied to E1, and so on, which is just the sum of this measure applied to each of the events in the disjoint union. So it therefore satisfies the countably additive property on disjoint unions. So this forms a measure. Of course, when one carefully goes through the theory of integration, one does have to justify that. But this is a well-known property of integration we use all the time, so it's fairly believable. Okay, so we've constructed this new measure. And what this shows is you can therefore very easily construct millions and millions of new measures. All you need is you take any function that is integrable, gives you a finite number, and once you have that, then you just construct a new measure in this way, and that will do it for you. So to show you an example, we just saw that, so here's like an example. If f of x is the function e to the negative absolute value of x, to use a very easy example, then if you integrate over the real line with respect to the Lebesgue measure, right, the usual. So Lebesgue measure just means you do this like a regular integral from calculus, the way you would interpret that. There's no tricks here. So that's why we mean Lebesgue measure, usual integration. Then we saw that this is finite. And the function is, of course, non-negative. So thus, we can construct a new measure, call it nu, sorry about that, and this measure of every Borel set is then calculated. So let's define it like this. It will be calculated as the integral over E of f with respect to the Lebesgue measure. So for example, let's say you wanted to find nu of the unit interval. Well, that would just mean that this is the integral over 0, 1 of, you would just write f of x dx. This is the way you would write it. So this would just be the usual integral of e to negative x, because x is non-negative here. So there's no need to use absolute value. And then if you calculate that integral, well, it's some number, right? It's some number. What would that be? That would be 1 minus 1 over e, I guess. Yeah, that's probably what it is. Okay, so that would be the measure of that interval. But you can easily modify this, right? You can easily go back to this example and modify this function. So instead of using e to the negative 2x, you can do e to the negative 2 absolute value of x. And it will still be the case that this will be integrable function with respect to Lebesgue measure, and then you can do the same thing again. And you can just keep on increasing this constant. This can actually be an arbitrary positive constant, and you have now an entire family of different measures, all derived by using this one single integrable function. But then there's nothing special about this function. You can take, for instance, you can take another function. You can take the function, let me just show you. You can take the function 1 over x squared plus 1. This function is non-negative. That function would be non-negative. And when you integrate this function with respect to the Lebesgue measure, you can recognize this. This is really the arctangent. This is arctangent between infinity and minus infinity. So at infinity, it would be pi over 2, and minus infinity, negative pi over 2. So this would integrate to pi, which is a finite number. So this function is integrable with respect to Lebesgue measure. By the way, the graph of this function looks like this. So it kind of diminishes down to 0. That's the graph of the function. And you're basically saying the area underneath this curve adds up to pi. Just a warning, maybe warning, to make sure we're not making the mistake. This is not the, maybe you heard of this thing called the normal distribution. This is not the normal distribution. Actually, the way we're going to be using the term distribution in our class will be a little bit different from how it's used maybe in undergraduate courses, but I'm sure you've seen a picture of this. It's not that. I know they look similar, but it's not that. The difference would be that the actual normal distribution, whatever it means, we will definitely get to that. The regular one, it looks very similar, but the difference is that it goes down to 0 a lot more rapidly. So the normal distribution that you're used to, maybe you do not know exactly how it is defined rigorously, or like the more careful mathematical properties of it, but I'm sure you've seen it. Maybe you've even seen it in some courses. It has what is known as thin tails. That means when you go further out, it's very, very small, whereas this type of curve, it does not go to 0 rapidly enough. It has thick tails. So they just look similar, but they're actually different. But the point is, this function is integrable, and because this function is integrable, we can then define a new measure, nu of a Borel set, to just be the integral. You integrate that function over that set, and it will calculate for you a measure for that set. So here's yet another measure that you can construct. So the point of this is, the moment you have one measure, you can construct lots and lots by integrating functions. So what's the point of this? So the moment you have a measure, you can construct many new measures by simply integrating non-negative functions. So that's what this shows. Now, a more interesting question to ask, so this is the question you can ask: is it true that every measure, every new measure, arises in this way? Right? That's kind of an interesting question to ask. So yes, you can construct lots of measures, but is it true that any other measure you can get in this way? So basically, we're asking this question. So this is really the question that we're asking. So we have x script a mu is a sigma finite measure space. Suppose nu is another measure on this pair. Is it true that you can express this measure as integrating some f. So does there exist a non-negative function, a non-negative integrable function? Let's say, yeah, non-negative integrable function with respect to the original measure, so that nu of an event is given by integration for all events. Is this true? So the answer here is clearly no, because there are two obvious obstructions here. But the amazing part is that if you eliminate these two obstructions, this is actually remarkably true. So what are the two obvious obstructions? The first one is that nu has to be a finite measure. And the second obstruction is, so why does this has to be a finite measure? Well, because we said this before, if you integrate it over any event, whatever this is a finite number, because by assumption, the function is integrable. So that will automatically have to be satisfied. So nu has to be a finite measure. And the second obstruction is, it is debatable whether you can call this obvious, but it's that, so the obstruction here is this, mu dominates nu. So what do we mean by dominate? It means this, that if mu of an event is equal to 0, then nu of that same event also has to be 0. So why is that? Well, because if you just write this out, nu of an event is the integral of your function over the event. But this should remind you of regular integration. If you're integrating something over a single point, something that has no measure, so this is something you say, measure 0. Intuitively, that is a negligible set, negligible. So as you know, in integration, if you have a function and you misplace a single number, if you take any point in the function and just misplace it somewhere else, you're just changing a function on a finite set. And if you change a function on a finite set, it's not going to affect the integral. So this is almost as if you're integrating over an empty set, because this is like measure 0. It's like integrating a function over a finite set. There's no area, right? There's no area. You think of it as area. There's no area there. So this is where, again, as I said, we're taking advantage of properties of integration. One of the properties of integration, which I think is fairly believable, is that if you have a set of no size, there's no area underneath the curve, because the actual set is of negligible size. So this integrable will automatically have to be equal to 0. Okay, so that's what it means for mu to dominate nu. The notation that is used is we write it like this. We write nu, and we do not write less than or equal to mu. It could be confusing. That might make it seem that if you calculate the measure here and you calculate the measure here will always be bigger than the measure there. So you do want to be careful with that. So the way we actually write it is we write it like this. It just means that if this measure is 0, then that one has to be 0. If the measure on this one is 0, then the measure on that one is 0. It does not mean that if the measure of this one is 5, then the measure on that set has to be 3. It could be bigger. The only time you can definitely come to that conclusion is if this measure is 0. So if that measure is 0, that one has to be 0. That's what I mean by dominate. So these are the two, you can say, obvious obstructions that prevent every measure from arising in this way. But the remarkable part is that these are the only two obstructions. And this is called the Radon-Nikodym theorem. This is pretty amazing theorem. So what the theorem would say is that if nu, so let's say it like this. So suppose x script a mu is a sigma finite measure space, and nu is another measure on this pair that is finite and is dominated by mu, then there exists a, and I'm going to put unique in quotation marks. It's very close to being unique. This is sort of unique in the sense of measure theory. You can probably guess what I mean by that, but for now I'll put it unique. There exists a unique non-negative function, a unique function non-negative function, which is integrable with respect to mu, to the original measure, with the property that nu of any event can be calculated as integrating this function with respect to the original measure over that event. And this is for all events in the sigma algebra. What do we mean by unique? So by unique, we mean that if g is another such function, then f is equal to g almost everywhere. What does that mean? i.e., if you look at the set when they're not equal, so if you look at the set of points, x in x such that f of x is not equal to g of x, then this set is of measure 0. It's a negligible set. So mu of this set, that's a negligible set. This is a set of measure 0. This is a set of measure 0. So the set of points on which these functions can disagree on is a negligible set. There is one small little complication that maybe the very observant student might be concerned about. You could ask this set that we're forming, how do you actually know that it belongs to the algebra? How do you know it belongs to the algebra? Because if we're calculating its measure, it better belong to the algebra, otherwise we cannot calculate it. So this is something I do not want to get into, but when we work with functions in, let's say, topology, we assume that our functions are continuous. In measure theory, instead of assuming that our functions are continuous, we assume that our functions are measurable. Now, what it means to be measurable will be explained in the next class. It's just not appropriate for this one. I don't want to make this too long. But you should understand that I am saying that whatever that function is, it has to be integrable. So if it's a function that is integrable, it automatically has to be measurable. Measurable function is necessarily integrable, but if it's integrable, it has to be measurable. Again, whatever that means. And so in the end, it just means that whatever set of points you calculate, this is a subset of X that will have to be in the sigma algebra. Okay, and so this F is unique, and it has a name. Let's make a definition. So under those assumptions, we call F so we're justified to use the word the. It is unique in a measure theory sense. So we call F the, very funny name, it's called the Radon-Nikodym derivative. And we write, this is the notation, we write that F is equal to, we write d, the derivative of nu with respect to the derivative of mu. The reason for this notation, you will see, I'm going to show you the page on Wikipedia that lists all of the properties, and you will see why this makes sense. But it also makes sense over here, because what are you trying to do? You're basically trying to solve for nu. Well, you have integration. How do you get rid of integration? You get rid of integration by differentiating both sides. So if you differentiate both sides, so if you do this like by using symbolic nonsense, you want to be able to say that this is true for every event. So in a sense, you're saying the indefinite integral, you're basically saying that nu is the indefinite integral of f d mu. Now, of course, this makes absolutely no sense whatsoever. This is just symbolic nonsense. But the symbolic nonsense is the heuristic, right? It's the heuristic for what we want to say. And then you would then differentiate both. I know we're completely abusing every piece of notation that it is, but that's kind of the heuristic for why we're doing it. And now if you differentiate that, you would end up getting d nu is equal to f d mu. And of course, this is nonsense and that is nonsense. But when you divide, which again, very suspicious, what do you mean by divide? But we're just doing it symbolically. If you were to divide, then you would say that d nu d mu is equal to f. Okay, and so you kind of erase all of these nonsensical lines and you just jump to the final conclusion. And this is your final conclusion. Your final conclusion is the derivative of nu with respect to mu is the f. So you define the derivative, you define this symbol by whatever that function is. That's the way you define it. So it's not like you're actually, I mean, in some sense you are differentiating. Later on when we see specific examples, it will feel like you're differentiating, but the definitions are set up to make sense. So this is just the notation for whatever that f is. And that's called the Radon-Nikodym derivative. And we will not prove this. We will not prove this. And if it bothers you, it's going to be simply because we will not need this. We will not need this. It's just something that's really nice to know. So we're going to be actually using, so maybe I should just go back a little bit. The Radon-Nikodym derivative is the converse to the construction. What do I mean by the construction? The construction is that you can construct new measures by using old measures and by integrating non-negative functions. The Radon-Nikodym theorem answers the question as a converse. Is it true that the new measures always come from such a process? So we will not really need it as far as I can tell. Maybe I'm going to make a mistake later on and we will need it, but as far as I can see at the moment, we're not really going to be using it. So this is why I'm not too bothered skipping over the proof. But I wanted you to see it because it's a pretty interesting theorem and it's just something that's nice to know. Let me show you the Wikipedia page to this theorem if you want to look up more about it. So as it says, this is a theorem in measure theory. It is used, of course, in probability theory. This is what we're doing. We're constructing a new measure by using integration. And now they do it a little bit differently from the way we're doing it. They're doing it in a way that's more general. I'm going to show you what I mean. So they start with a measure space, and they have two sigma finite measures. Now, the way we're doing it, our original measure is sigma finite, and the new measure, nu, is finite. But they're assuming that they're both sigma finite. And they're saying, suppose mu dominates nu. They're using a different terminology called absolutely, that this means exactly what we mean. I'm not a fan of saying absolutely continuous. I think it just makes, from a language point of view, to say that mu is the one that dominates it. So then there exists, now instead of saying integrable function, they say a measurable function. So there exists a measurable function, whatever that, we will define that, by the way, next class. There exists a, it's just in this class we do not need it. So there exists a measurable function such that, you see, they're not saying integral function. They're saying there exists a measurable function such that this holds. And they allow the possibility that the integral could be infinite. The function is non-negative, so when you integrate it, if it's not integrable, it will just give you positive infinity. So they do allow the possibility that their measure could become infinite. That's why they're writing it a little bit differently. We're writing it with the assumption that it's an integrable function, simply because I did not want to define what it means to be a measurable function, but we'll do that next class. And then they talk about the Radon-Nikodym derivative. They say it is unique up to a null set with respect to mu. So they're equal almost everywhere, and this function is denoted as a derivative like that. And let's see, we keep on going. Okay, so here are the properties. So these properties are very interesting. So if you assume that v and mu, nu and mu are dominated by lambda. So here lambda could be a Lebesgue measure on the real line, but it could be a measure in general. They're dominated with respect to lambda, then the derivative of the sum. Now the sum over here is just referring to the sum of the two measures. You can take the sum of two measures. It's then equal to the sum of the derivatives. And that, here's another very interesting one. This is the chain rule. This kind of justifies the reason why this notation is fantastic. That if, as you can see, if lambda dominates mu and mu dominates nu, then if you were to differentiate nu with respect to lambda, you can first differentiate it with respect to mu, then multiply it by differentiating with respect to lambda. Here, you're not multiplying measures, you're multiplying functions. So you have the chain rule. Then you have flipping it over. You also have integration by substitution. That's another interesting one, which is not surprising. If you have a chain rule, you have integration by substitution. That if you integrate, as it said, if you integrate some function with respect to mu, you can integrate that. That's the same thing as integrating that function multiplied against the Radon-Nikodym derivative, but this time you use the other measure. Then there's something called sign measure, which we do not need. This is when a measure is allowed to be plus and minus infinity, but it's supposed to have some other properties. Let's not go there. So that's just something that's quite interesting. Okay, so let's just return back here again. Let me just, so now I'm going to give you an example of something that does not have a Radon-Nikodym derivative. So in a sense, it does not exist because one of the two obstructions will get in the way. Now we have an example. Delta zero, so this is the Dirac measure, whose point mass is located at the origin, is not dominated by Lebesgue measure, lambda. So dominated would mean that delta zero, this is the notation that we use, and we're saying that this relationship is not true. Why not? So consider the event, which is the singleton event, and it contains the origin. this is an element of the Borel algebra on the real line. So clearly, the Lebesgue measure of this event is 0 because this is a degenerate interval of length 0. But the Dirac measure on this event, because the Dirac measure is concentrated at the origin and the event contains the origin, the Dirac measure is equal to 1. Therefore, this relationship is violated. The Lebesgue measure is 0, yet the Dirac measure is not. So this shows that the Dirac measure is not dominated by lambda. So in particular, the Rodin-Nikodym derivative, so if you were to look at the derivative of delta 0 with respect to the Lebesgue measure, does not exist. What does that mean? It means that, i.e., there is no function. There is no function. So this is a real valued function f that is non-negative, so that the Dirac measure of any event, let's call it f. I do not want to use e again because we already used it. So that delta 0 of f can always be evaluated by integrating over f this function with respect to the Lebesgue measure for all capital F in the Borel algebra. So it is not possible to get the Dirac measure as the integral of some non-negative function. Now, I want to show you something that is interesting, but it's not important for us. So physicists invented a function, and maybe you've seen this before, called the delta function. And this function is defined by the rule that delta of a real number is equal to infinity if x is 0, and it's equal to 0 if x is not 0. So the graph of this function, so if this is x and this is delta, then the graph of this function is it's 0, and then at the origin it spikes all the way up to infinity. And it has the property, this function has the property that if you were to integrate this function over f, then the integral will be equal to 1 if 0 is in f, and it would be 0 if 0 is not in f. So this is like the singularity, and it depends where this f is. So let's just, for simplicity, think that f is an interval. So if this is f, then because this singularity is not in the interval, this function will integrate to 1. And if the interval includes the origin, this is where we have the singularity, then it will integrate to be 1. Okay, so the idea is that the function is infinitely concentrated at the origin, and it properly integrates it the way that you want. Now the thing is that such a function, hence why I put it in quotation marks, because it does not really exist. Well, maybe I should not. Maybe I can just say such a function does not exist. First of all, it violates our previous theorem that in order to be able to express the Dirac measure in terms of an integral of a function, it's both necessary and sufficient that the Dirac measure is dominated by the Lebesgue measure, which it is not. So that would contradict the theorem. But also, if you think about it, when you're integrating functions, what a function does at a single point does not matter. Even if you were to set the value at the origin to be infinity, it would still mean we have that if you were to integrate, let's say from negative infinity to infinity, delta x dx, that's the same thing as integrating the zero function. Because changing a single point in an integral does not change the value of an integral, even if it's infinite. And so you would get that it has to be equal to 0. So such a function does not exist. But here's something that's interesting. Nonetheless, physicists still use the properties of delta. And you might ask, why are they allowed to do this? Well, the reason is actually quite simple. So, the delta function is primarily used to solve various PDEs. It's not actually used in probability theory. It is used to solve various partial differential equations that come up in physics. And for those purposes, interestingly, even though the delta function is not a valid function, it still leads to the right answer. Because what physicists use the delta function, they have a very good intuitive feel for what it is supposed to do. And when it is interpreted in that way, it kind of makes sense what it's doing. Now, some people with a math background, they look at this and they get bothered. And they would say, well, you're abusing mathematics. And it is true, you are abusing mathematics. However, I think the more appropriate attitude to have, if you are a mathematician, is to rather ask the question, you want to ask, how can we place a rigorous foundation on the delta function? So if you're mathematically minded, this is the way you're supposed to be thinking. You do not want to have this kind of attitude where you see physicists do something that is an abuse of math that we know, but it works and it leads to the right answers and the right calculations, and then disregard the whole thing. Physicists have good intuition, and math and intuition is the guiding principle of mathematics, that when we come up with mathematical theories, we always have some intuitive idea, and then we try to make it rigorous. The intuition always goes first. When you come up with a proof, you need to have an intuition for what you're trying to prove. So the intuition always goes first. And a good mathematician is someone who can balance rigor and intuition, how to take those ideas and make them rigorous. So this is the correct attitude to have. So sometimes it's interesting to see the way people in physics abuse mathematics, but you should be impressed by that, and you should really be asking the question how you can create a foundation for that. And for those of you who might be interested, a foundation for this delta function was developed in the 1950s. And nowadays, this is a very important part of modern analysis. And it turns out, to give a very quick answer, it has absolutely nothing with what we're doing this semester, but for those of you who might be interested, the delta function is not a function. It rather is what they call a generalized function. That's one way to define it. So it's not as a function, it's a generalized function. And from that point of view, you can use it and you can explain more carefully its properties and why they're justified and things like that. But I just bring it up because we are talking about the Dirac measure, and maybe some of you have heard of the Dirac delta function, and we're using delta over here. So it's reasonable to ask, is there a connection? And here there is a connection, because the idea is that the delta function from physics plays the role of the Radon-Nikodym derivative with respect to the Lebesgue measure. But of course, it does not exist as a function. You rather have to change your understanding of what you mean by a function in order to make that work out. But anyway, so we have this. Now, getting back to probability theory, the next thing I would like to talk about is, I'm going to make this definition. We say that a probability measure on the real line with the Borel algebra is discrete. So this is what we call a discrete measure. If and only if we can find a non-empty subset of the integers, finite or countable, and real numbers, positive real numbers with n coming from the indexing set and points on the real line, so that the probability measure can then be expressed as a sum of these Dirac deltas. So you would say an delta Pn with the coefficients adding up to 1. This is what we call a convex combination. Why it is called a convex combination, let's not go there. It's just a name. If you know anything about convex sets, maybe you're familiar with that terminology, but for us, that's just a definition. So convex combination is when you have positive numbers. You can allow non-negative numbers, but if any of them are 0, you can just drop them out. So you can just assume they're all positive and they add up to 1. So you say, so basically, right, so basically P is discrete if and only if it is a sum of point masses. So point masses are exactly these Dirac deltas that are concentrated at a single point. So that's the definition of what it means to be a discrete random variable. Now, there is another definition, which you can argue is perhaps more elegant. So equivalently, and maybe we can state this as a proposition, and I'm not going to prove this because we do not really need it, but maybe this is a good homework problem, is you can show that P is a discrete probability measure on the real line with the Borel algebra if and only if the following property is satisfied. So if you were to take the sum, if you were to evaluate the probability measure at every point on the real line, then that would add up to exactly 1. Now, I know what some of you might be thinking. Some of you might be thinking that this is uncountable. How can you take a sum of uncountably many things? If it's a countable sum, then that's just an infinite series. But how do we take an uncountable sum? Well, it turns out, so this is called point mass. This is called point mass. So if the probability of a singleton set is positive, that's called having point mass. And part of the homework question is to show that every probability measure, no matter what you put, every probability measure, I'll write it over here. So part of this exercise is to show that any probability measure has at most a countable number of point masses. So what this means is that even though it looks like it's an uncountable sum, almost every single one of these is going to be 0. So you're going to disregard them, and you're only going to look at the ones that are positive. Okay? So if the positive ones add up to exactly 1, and not less than 1, but to exactly 1, then you're dealing with a discrete measure. So I think you can argue this is perhaps a more elegant way to summarize what a discrete measure is, because then you do not have to make these choices. But it turns out it's completely equivalent to this. So this is what we call a discrete measure. Now, another type of measure that we have is what we call absolutely continuous. So let's take this down. Definition, we say P, and this is a probability measure on the real line with the Borel algebra, is absolutely continuous. So we do not say continuous, we say absolutely continuous. If and only if P is dominated by the Lebesgue measure. So i.e., that means that the Radon-Nikodym derivative exists. So what does that mean? I.e., there is a function f, a non-negative real-valued function with the property that the probability of any event can be calculated by integrating this function over that event with respect to the Lebesgue measure for all events in the Borel algebra. So that's what it means to be absolutely continuous. So this function, it has a name. So this function, this is called if you've taken a course in probability theory, that's what it's called. This is called the probability density function for P, for this measure. Sometimes you denote it as the PDF, probability density function. In an undergraduate course, if you learn about probability density functions, this is not the way it is taught for you, because this would be too advanced. This would not really make sense on an undergraduate level. But this is, one can say, the more rigorous way of defining what we mean a probability density function. So basically, basically, we say a probability measure P is, so we do not say continuous, we rather say absolutely continuous, is absolutely continuous if and only if we can find a function that integrates to the measure, that integrates to P. So what do we mean more carefully? Well, a function cannot integrate to P, but you can evaluate P on events, and if you integrate that function over the event, then it will coincide and it will give you the measure. And such a function is called the probability density function. Let me give you an example. So let me take this down and give you an example. And I'll give you intuition for this example. So let f be the function f of x. It's going to be equal to 1 if x is between 0 and 1. It's going to be 0 if otherwise. So here's the graph of this function. On the interval from 0 to 1, the function is equal to 1. And off that interval, it's equal to 0. Now, you may wonder what happens to these endpoints. Do you set the function equal to 0? Do you set the function equal to 1? Do you set the function equal to a half in between them? It really does not matter, because we're going to be integrating this function. And when you integrate this function, it's not going to make any role whatsoever. Then observe that f is a probability density function. Why? Well, since the function is non-negative, no matter what value of x you pick, f of x is 0 or 1. And when you integrate this function on the real line, f d lambda, which is another way of saying you just integrate. Since the function is 0 here and 0 here, and we do not care what happens at the endpoints, it does not affect the integral. This is really the same thing as integrating from 0 to 1 of the constant function 1, but that integrates to 1. So we have a function that is non-negative, and it integrates to 1. So what does that mean? So thus, hence, we can use this function f to construct a probability measure on the real line. So let's call this probability measure P. So we would then define P of an event to be equal to integrating the event against this function f. That's the way we would define it. So for instance, let's say our event is all the way out here. This is our event. So then it's clear the probability of this event taking place would then be equal to 0. Now, if the event is part inside, is like, let's say, part in here and part in there, you would disregard the negative part and you only focus at the positive part. Okay? And when you integrate this, you're just going to get the length. The only part that will matter is the length of the interval to find the area underneath the curve. If the event is completely contained, then you would, when you calculate the area underneath the curve, the height is equal to 1, and so the probability would just be determined by the length of the interval and nothing more. Okay, so intuitively, what does this represent? So intuitively, this triple, so this is a probability space. A probability space consists of a sample space, it consists of a sigma algebra, and it consists of a probability measure. So those three pieces of data defines for you a probability space. So this probability space would then describes a random experiment that produces a random number between 0 and 1, because you can see that if the event is outside 0 and 1, integrating that will result in 0. So it produces a random number between 0 and 1 in a uniform manner. Basically, we want to say that all points between 0 and 1 are equally likely. But of course, this is nonsense. The reason is because the probability, so since the probability of a singleton is always 0, this is not like the Dirac delta where you have point masses. If you have a singleton and you integrate over a singleton, that's going to be 0. So picking a random number between 0 and 1, no matter what you pick, it will always occur with probability 0. So rather, instead of saying that the points are equally likely, which is nonsensical because they all have probability 0, you rather want to say that this random experiment produces for you numbers in a uniform manner. So here's the way you can visualize this. You're going to draw the interval from 0 to 1 like this, and then you're going to pick a random number, let's say over here. You do the random experiment again, and you get another random number. You do a random experiment again, you get another random number, and then you get another random, and so on. And if you do this experiment like 1,000 times, one thing you will notice is that these random numbers that you generate, they're all equally spaced apart. They're not going to be concentrating anywhere in the middle or anything like that. They will all be equally spaced apart. So it has to do with the fact that this is a completely flat line, that it has no preference of whether you are in the center or you're on the edges. So that's what this represents. Okay, and this is a important random variable. I'm sorry, let me take it back. Let me not say random variable. We're going to talk about random variables next class. Let me take it back. Pretend I did not say that. This is an important probability measure. This is called a uniform measure. So this P is called the uniform probability measure. And the notation that we can use is we can say that P, we kind of write it like this. This is the way we say it. We say that P follows the uniform. So this just, you can kind of say follows the measure of uniform 0, 1. That's the way. So this is just a notation. You say that P, so P is a probability measure. What can I tell you about the probability measure? It is uniform on 0, 1. This is supposed to represent that P has a probability density function. How does the probability density function look like? You're going to draw the interval from 0 to 1, and then you make it uniform. You make it completely flat. You do not really care about the endpoints, so that's why we do not write open or closed. And it's not a big deal. It's not going to affect anything because the integral is going to be unchanged. But you can generalize this. So more generally, we're a little bit more general. We would say that P follows a uniform measure on the interval AB. So here, A is strictly smaller than B, and these are finite. So we do not allow plus or minus infinity, finite real numbers. More generally, P follows the uniform measure if and only if. So this is a definition, right? This is the definition. The probability density function, which is the Radon-Nikodym derivative with respect to Lebesgue measure, is the function which is, so it's going to be 0 if otherwise, and it's going to be if x is between a and b. And instead of setting it equal to 1, that's not what you're going to do here, because you need something that integrates to 1. So the correct way to do it is b minus a, because then the rectangle will have width matching with the reciprocal of its height. So as a picture, this would be a PDF. So this would be a, this would be b, and then you properly rescale it. So the wider the base is, the less tall the function would be, so that it properly integrates to 1. So this is what the probability density function would be for such a measure. This is what we call the uniform measure. Now, I want to give you another example. I want to give you a very simple example of something that is not uniform. Here's another example. Let f of x be the function that is 2x if x is between 0 and 1, and 0 if otherwise. So as a picture, your function would go like this, and then over here it's 0, and over here it's 0. And between 0 and 1, it goes up like a line with slope 2. And we do not care what it does at the endpoint. So then you can construct a probability measure as follows. The probability measure of an event would then be integrating the event of this function with respect to the Lebesgue measure. So what is this supposed to represent? So intuitively, this triple, so if we take the real line, we take the Borel algebra, and we take this probability measure, will represent a random experiment that produces a real number between 0 and 1, but it is more favorable to produce a number closer to 1 than 0. So if you were to draw the number line from 0 to 1, and you were to do a random experiment, maybe that would be your first point. Maybe this is your second point, your third point, your fourth point. And as you will see, there's going to be a lot of points over here, and then here you might have like a few or something. Here you do not have that many, and most of them, you'll have a lot more. So if you were to cut it down the middle, so if you were to cut this down the middle, and you do this like 1,000 times, you will see there's a lot more over here than over there. In contrast to when we have uniform measure, where the random experiment does not care where you are on that interval. It's uniform. It's the same throughout. This one is more favored to be to the right side. Now, we're not going to say that the points on the right are more favorable than the points on the left. We're not going to say that because we're not going to say they're more probable than the points on the left, because a single point will happen with probability 0 nonetheless. But it's rather should be interpreted like this, that if you cut it up into small little subintervals, that the ones that are to the right will occur more frequently than the ones that are on the left. Now, you should notice that this integrates to 1, right? This is a triangle, and the area underneath the triangle, this is 1, and that's 2. So the area is 1, which it's supposed to be if this is a probability density function. And the other thing that I wanted to point out that you might find very unusual is when you're talking about discrete measure, the sum of the point masses, well, the sum of the weights of all of the point masses have to add up to 1. So in particular, the values, all of the weights individually cannot exceed the number 1. Whereas this might seem a little bit unusual because it does go above the number 1, right? So this would be 1, and you can see it actually goes above the number 1. Could a probability density function go above the number 1? Yes, because when dealing with probability density function, this does not represent the probability, this represents something else. And if you want an intuition for what that represents, one way you can interpret this is if you were to pick something, so if we go back to this number line again, and you were to pick, let's say, something that's very close to the far right, that point, and I ask you what's the probability of landing on that point, the correct answer is that happens with probability 0. You do not take its location and multiply it by 2, because otherwise that's not going to make sense. If that point is at 0.9, the probability is not 1.8. Rather, it means the following. What it means is if you were to draw a little interval around it, this is an infinitesimal interval of thickness epsilon. So let's say epsilon is 0.001, tiny little subinterval. So now because you have a small interval that has thickness to it, now you can ask the probability of landing in that event. And the interpretation here would then rather mean that you would take 0.9, where the infinitesimal interval is centered, and that would be 1.8. So that does not mean that the probability of landing in that interval is 1.8. That rather means it's 1.8 times more likely to land in that little interval than the length of the interval itself. So if, let's say, the length of this interval was 0.01, then the probability, so actually let's say it's 0.1 to keep it simpler, then the probability of landing in that subinterval would be roughly 0.18. I'm sorry, if this was located at 0.9. So you would double 0.9, so that would give us 1.8, and then you would multiply by the thickness of the interval, which is 0.1, and you would end up with 0.18. So the probability of landing in that little infinitesimal subinterval would be roughly 0.18. That's the correct way to interpret that, because individually the points have no probability. So that's what this probability density function is supposed to represent. Now, we do not really have time to talk about this. So you could ask the question, so is it true that all probability measures on the real line with the Borel algebra are either discrete, or we're not going to say continuous, the technical terminology is absolutely continuous. So these are the ones that have a probability, so these are the ones that have a probability density function with respect to Lebesgue measure. And the answer is no. You can do a very silly example where you take a convex combination between something that's discrete and something that's absolutely continuous, but then you can say that sort of silly example, is there something that's genuinely different? So the simple answer is there's another type of probability measure, and it's called singular. And then there is a classification theorem in probability theory that says that every probability measure is a convex combination of those three types. This is actually not important, as far as I know. With my knowledge of probability theory, I have never seen this used ever. Now, it would be funny as the semester goes on, we'll realize we actually need it. But as far as I know, I've never seen anyone ever use this. It's an interesting theorem because if you're interested in the foundations of probability theory, it's interesting to ask whether you can come up with other types of probability measures that are neither one of these two, and you can. And then there's a classification theorem for those. And it feels like it's something that should be important because it's a classification theorem. Usually in mathematics, classification theorems are really important. But here it really does not do anything for us. And the reason for this is actually quite simple, because in probability theory, the kind of probability measures we deal with exclusively are either in the discrete family, which are actually very elementary to understand. You do not need any measure theory to work with those. And the ones that are a little bit more sophisticated is the absolutely continuous family. Those are the ones that have PDFs to them. So those are the ones that are a lot more important. And that's why the classification theorem almost never comes up. It's just something interesting to think about. And we also never really mix these two together either. I've never seen them where it's important to consider some combination of those two simultaneously. But what is actually important is I want to discuss what is perhaps the most important PDF in probability theory. This is perhaps, one can argue, so this is perhaps the most important PDF in probability theory. So let's give this a name. I do not know what to call it, so let me call it lowercase phi of x. And this is going to be equal to, by definition, is going to be the following function: 1 over the square root of 2 pi e to the negative x squared divided by 2. Okay, now this is very ad hoc. It appears out of nowhere. Like historically speaking, do you really think that one day a mathematician just written down that function and that was the end of it? Of course not. There was something that led to such a PDF. So later in the course, later in our course, we will see how this function arises. But for now, let's just talk about this function so that when it arises, we're going to be comfortable with it. So first of all, there is a proposition. And the proposition is that when you integrate this function, it actually integrates to 1. This is not obvious. Because if you try to calculate the antiderivative of this function, this is one of those functions that does not have any simple antiderivative formula to it. So you have to use some kind of tricks in order to justify why this function integrates to 1. So this is actually the reason why you put this constant. If the constant was not here, then it would not integrate to 1. So you have to actually put the constant there so that it integrates to 1. So you have to check this. And I'm going to just put this on the homework. This is a very famous calculation in calculus. I'll give you a hint how to do it if you've never seen it before. I imagine many of you have probably seen it. It's a very common trick. You basically, you kind of square the integral, and then you turn it into polar coordinates. And then from there, you can get the answer. Okay, so this is a probability density function, and here's the way that it looks. This is the one that you see on the front cover of every probability book and every book on statistics. This is the one that appears in every front cover. This is the one that goes like this. And this one has what you call thin tails. That means it decays extremely rapidly because you have an exponential, a square of an exponential, so it decays extremely rapidly. So this is the curve that you always see. This is the function that describes this curve. And like I said, for now, we just accept this. But later, we will derive where the function comes from. It's not just made up. There's a process that leads to it. We just have to wait and see what that is. Also, okay, we use the notation. So here's notation. If P, so we use the notation, we write that P, and this is a probability measure on the real line with the Borel algebra. We write that P follows the measure of normal 0, 1 if and only if the probability density function of P is this function lowercase phi. So in other words, i.e., the Radon-Nikodym derivative with respect to the Lebesgue measure is this very special function that we're calling phi. I'd like to just quickly finish. Now, you will notice I'm writing normal 0, 1. Remember we talked about uniform 0, 1? So this suggests that can you have normal with different numbers, like normal 1, 2? Can you have that? You can have that. You actually have a family of normal measures. There's an entire family of these. And this is just the one that's most important, because every other normal can always be rescaled back to this one. So this is the reason why we care about this one the most. It just keeps the notation simpler. The last thing that I want to finish with is this. So let us say, so suppose E is an interval, and P is a probability measure that follows normal 0, 1. How to compute the probability of an event? Well, so let's say that E is the interval from A to B. For simplicity, we can assume that it's a finite interval, though it doesn't really matter. Everything that we're about to say will also make sense if it's an infinite interval. So let's say it's a finite interval, and we do not care whether or not we include or exclude the endpoints, because when you integrate, it's not going to matter. Then the probability of E would be the integral over the event of this function with respect to the Lebesgue measure. But if you write it out, this is 1 over square root of 2 pi integral from A to B, e to the negative x squared over 2. And the question is, how do you do this? How would you compute something like this if this is not a function that can be easily integrated? So this is what we do. We introduce a new function. Let's call it capital phi. And capital phi of x would be the integral all the way from negative infinity up to x. And it's the integral over this phi. So if we write this out, so let's write this out using a different variable. So this would be 1 over square root of 2 pi. And this would then be e to the negative y squared over 2. So as a picture, we go back to this, what we call normal curve. And if we have an x, we calculate the area up to x. So this is going to be phi of x. So that's the first thing that we do. And then we observe that phi of x. So if you want to calculate the area up to x, you first calculate the area up to the midpoint. That would be 1/2. And then that would be integral from 0 to x of this. Okay? And now you use, so phi of x is equal to 1/2 plus. And what you do next is you use repeated integration by parts. And I'm going to put this on the homework for you. This is actually very easy. It's a nice computation. If you use integration by parts repeatedly, you're going to end up with this. You're going to end up with phi of x, and then it's going to go like this. So I'm writing this off the top of my head, so I could be incorrect. So I think it's x over 1 plus x cubed over 3 factorial plus x 5 over 5 factorial plus x 7 over 7 factorial, and so on. No, I think it goes like this. It's double. It's really it's okay. It's 1, 3 times 1, 5 times 3 times 1, 7 times 5 times 3 times 1. So it's like a factorial, but you skip every other one. So the notation that you use here, it's 3 double factorial. Double factorial, it's like a factorial, but you skip every other number. So it's very similar to the infinite series for sine, except it does not alternate, and instead of factorials, you have double factorial. So there's a nice pattern here. And the point is that now that you have this infinite series, you can calculate this like numerically at any number that you want. So if you want to find phi of 1, you would just put 1 into the infinite series, and of course you would go as far as when these fractions become rather insignificant, and then you calculate what that is. So typically you would do this on a calculator. So if you want to do this using a calculator, so on Wolfram Alpha, so you can use Wolfram Alpha to do this for you, so you do not have to do this by hand. So on Wolfram Alpha, the command, this is the way you would type it in. So if you want to, let's say, find capital phi evaluated at 1, let's say, you would just type in standard normal. So standard normal, it's when the normal is 0, 1. That's the most important normal. As we said, there's different types of normals, but this is the most important one, standard normal. Then you would write CDF. So CDF stands for cumulative distribution function. So it's just cumulative. You're accumulating everything up to x. So you would just type in standard normal CDF of 1. And if you type that in and you click enter, the calculator will compute out the number for you in case you actually care to know what that number is. So that's the way you calculate it out. And now that you have capital phi of x, the way you would compute this capital phi of x is this would then just be capital phi of b minus capital phi of a. So how do you get the area between a and b? You first calculate the area from negative infinity up to b, and then you subtract the area that you do not want. That's the area up to a. So that difference will then calculate for you the area between a and b. So this is the way you will calculate the probability of an event using this probability measure. So if the probability measure follows the normal 0, 1 family, which is also called standard normal, there's also non-standard normals where you would use different numbers, but they're not as important. So if you're following standard normal, so if this is the standard normal measure, then the way you would then calculate the probability of an event, let's just assume the event is an interval. So the way you then calculate the probability of the interval is you will integrate this function lowercase phi between those two numbers. But to integrate that, you're going to use capital phi, and you're just going to subtract capital phi at the endpoints. But then how do you calculate capital phi? You calculate capital phi. This is one way to do it. This is lowercase phi, by the way. This is one way to do it. And it's on your homework to derive this infinite series. It's just integration by parts repeatedly, and it will immediately present itself. I might be incorrect about this. I'm just writing this off the top of my head. I think that's the way it goes. If not, it'll be corrected on your homework. So this concludes. Oh, and unfortunately, I do have to apologize. We ran out of time again in defining the Cantor set. I kept on saying there's this very bizarre, interesting set that is nice to know for measure theory and real analysis called the Cantor set, but we again ran out of time. We do not want to keep these lectures too long. They already are long as they are. But this lecture, we talked about probability measures and also measures on the real line. And in next lecture, we're going to then go on and talk about random variables.